Hey everyone, welcome back to another lesson in MCR3U. Today we'll be looking at applications specifically of sine and cosine, which are trigonometric functions. So to start here, there are many applications of trigonometric functions, such as sine, sound, light, tides, Ferris wheels, pendulums, and springs, and they can all be modeled with sinusoidal graphs. In fact, anything that is periodic may be modeled by some combination of these trigonometric graphs. So if we look at this first example, we see here that the Ferris wheel has a radius of 45 meters. So it has a radius of 45 meters, and its center is 50 meters above the ground. A complete rotation takes 20 seconds. And again, we're going to suppose the graph starts when the rider is at its lowest height. Okay, so when we look at this, there's a couple things that we can see here. First, again, we know that it has a radius of 45 meters. So in here it has a radius of 45 meters. So we can indicate that in the diagram below. So here and here. Okay, what we can see here is that, again, it's from the center to the maximum and the center to the minimum. And we've seen that that would represent the amplitude. So here we see that the radius of 45 meters will represent our amplitude. Here we see that the center is 50 meters above the ground, and that will represent our axis. So here we have center is 50 meters above the ground. So here that will represent our axis of the center, again, which is going to be 50 meters. And then a complete rotation, so a full rotation takes 20 seconds, and that's going to represent our period. And then again, we're supposing that the graph starts when the rider is at its lowest height. Okay, so here, again, other things we can label here. Here we can see that, again, it's 45 meters, and the gap to the ground. And here we see that, again, a full rotation takes 20 seconds. Again, so a quarter of a rotation here will take 5 seconds. So here, if we list the information that we have already, then our A value, which is our amplitude, again, will be given to us as 45. Our, our axis will be y is equal to 50. You see here that our period is equal to 20. And so here, if we find our k value, we know that our k value is equal to 360. 360 over 20. And so here, k is equal to 18. Okay, and so here, if we, again, are finding equation using the base function of y is equal to sine x, again, we'll represent a few things. First thing we'll do is we'll let h represent height in meters, and e is time in seconds. Okay, so here we're given our graph on the right. So here we see that, again, it starts at a minimum, and then gets to a maximum at 10 seconds, and then back to the minimum at 20 seconds. So that we can label as t, which is our time, and then here will be our height. And here we see that, again, for our sine graph, again, remember our sine graph then initially usually starts at 0 and 0, but here it has moved 5 to the right, so that here we see that d is equal to 5 to the right. So here we see that, again, when we write our transform sine function, it's y is equal to a sine k theta minus d plus c. Here, in terms of h and t, so h of t will be equal to 45 sine, c value here is 18, e minus, and then our d value is 5 plus, and our c value is 50, which is, again, our axis here. Okay, and here it says find the equation using the base function y is equal to cos x. And so here we see that there is a reflection in y is equal to cos x since it starts on the minimum. And here the original cos graph, again, will start on the maximum. So if it starts on the minimum, then we see that there's going to be a reflection. So here we write, h of t is equal, again, our amplitude, again, now with a reflection, so negative 45 cos. Our k value is 18 still here, so 18t. Again, no phase shift if we look at our cos graph, because it starts again at, again, 0, initially starts at, again, 0 as well in terms of y is equal to cos x. So here, no phase shift. However, again, our c value here is going to be plus 50. Again, if you look at this reflection here, we can write it as h of t is equal to negative 45 cos 18t plus 50. If we treat it, again, without the reflection, then we can indicate that there is a phase shift. Again, if we want to start it at the maximum, Again, that means that here the maximum starts at 10, which means that it has shifted 10 units to the right. So we can also write it as h of t equals 45 cos. Again, we're going to assume no reflection here. We're going to assume the phase shift. So 45 cos 18 t minus 10, because you moved 10 units to the right, plus 50. So two ways to write this equation. Part C says, how high is the rider after 17 seconds? So here we can simply just sub t is equal to 17 into the equation. Here again, h of t is equal to 45 cos 18 e minus 10, so it's 50. We'll sub in 17 for the values of t. So here we have 45 cos 18, 17 minus 10 plus 50. And here we see that h of 17 will be equal to 23.549. So we'll round it to two decimal places. So here, therefore, after 17 seconds, the rider is 23.55 meters high. Okay, question part D of this example says between 0 and 20 seconds, when is the rider 30 meters off the ground? So here we see that again from 0 to 20 seconds, that would be our first cycle. So here we want to see again when h of t is equal to 30. And so here if we write our equation, again we have h of t is equal to negative 45 cos 18t plus 50. So these questions, again, because there's different ways to represent the problem, you can use any of the different equations to solve for these values. So here we're just using, again, the different ones we used, 45 cos 18t minus 10 plus 50 for part C of this example. And here we're using negative 45 cos 18t plus 50 for part D of this example. So here we see that, again, 30 is equal to negative 45 cos 18t plus 50. And here we, again, are solving for t. So here we have 30 minus 50 is equal to negative 45 cos 18t, negative 20 over negative 45 is equal to cos 18t, 4 over 9 is equal to cos 18t. And here what we'll do is we will let 18t be b. And so here we have 4 over 9 is equal to cos b. And so here if we draw a grid, we see again that if we look at our cast rule, we know that cosine is positive in quadrant number 1 and quadrant number 4. So here we see that quadrant number 1 and quadrant number 4, and cosine is the adjacent. So here this would be 4 over the hypotenuse. And so that would be the diagram that represents it here. So here if we look at it in quadrant number 1, we see that cos -1 of 4 over 9 will be equal to b. And so here, b is approximately equal to 64 degrees. And so here, if we sub back in b for 18t, so here this will be b1. So here we see that 18 t1 will be equal to 64. Here we'll divide both sides by 18, so t1 is equal to 64 divided by 18. And so here t1 is equal to 3.56. If we look at it in quadrant number 4, here we see that and b2 is equal to 360 degrees minus our beta value. Again, we saw that beta was 64 degrees. So b2 is equal to 360 minus 64. And b2 is equal to 296. We'll sub in again 18 t2 is equal to 296. And so here t2 is equal to 296 over 18. So here t2 is equal to approximately 16.44. And so here what we can see is that therefore then the rider is 30 meters above the ground, 3.56 seconds, and 16.44 seconds. Okay, and then lastly, it says find the equation for the motion of a rider if the graph begins where the rider is at the highest point of the Ferris wheel. Okay, so here, if we look at our graph, if we drew this, again, find the equation for the motion of the rider if it begins where the rider is at the highest point, starts at the highest point, goes to minimum, and then back to the maximum. So here, then we would see that h of t would be equal. So our amplitude will still stay the same, 45. But again, this time it starts at a maximum. So if we look at it in terms of cos, it'd be 45 cos. K value is 18t plus 50. And then there'd be no phase shift here.